Pluto is a far-off and puzzling midget planet, which was once a member of our solar system's planetary family. However, recent surprising announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They propose that this cold world is on a potential crash course with Neptune. Yet, how might this occur, and what might be the consequences of such a gigantic event? Are we seeing an intriguing astronomical phenomenon? Or is there something else to this looming cosmic crash? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partially due to its curious orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential dangerous collision between these two planets that could pose a gigantic threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, straying significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these complexities is a testament to the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem explains how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms apsidal libration and axial libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is an overall libration. Concerning Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Axial libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an additional layer of safety from potential collisions. Another critical component in this scenario is the VZK oscillation. This is named after three scientists, von Zeipel, Litov, and Kozai, who studied how objects move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems chaotic, this oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even if things in space seem wild and random, some patterns and rules keep everything in order. These components help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or get thrown off course. This three-body problem helps in understanding how these paths change due to how these space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is indeed chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over remarkably long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the large planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path stable. Yet, Neptune is not the only one helping. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and stable, and Saturn helps too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a very long time, even billions of years. So, it's like Neptune, Jupiter, and Saturn are working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential in the context of the universe for maintaining the order and consistency of space bodies' movements. Without these elements, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks of it potentially colliding with Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Pluto's status as a cosmic enigma continues to captivate astronomers and space enthusiasts alike. Discovered in 1930 by Clyde Tombaugh, Pluto was initially hailed as the 9th planet in our solar system. However, its classification underwent a significant revision in 2006 when the International Astronomical Union redefined the criteria for what constitutes a planet. Pluto, due to its size and characteristics, was reclassified as a dwarf planet, sparking debates and discussions about its nature and place in our cosmic neighborhood. Despite its reclassification, Pluto remains a crucial object of study in the field of astronomy. Its unique orbit and relationship with Neptune have particularly intrigued scientists, prompting extensive research and theoretical studies to understand its dynamics and potential interactions with other celestial bodies. The discovery of Pluto was a significant milestone in the history of astronomy. Clyde Tombaugh's meticulous observations from the Lowell Observatory in Flagstaff, Arizona, led to the identification of a faint, moving object beyond the orbit of Neptune. This discovery not only expanded our understanding of the outer solar system but also raised questions about the nature of Pluto itself. Initially, Pluto's size was overestimated, leading to its initial classification as the 9th planet. However, subsequent observations and advances in astronomical techniques revealed Pluto's modest size, comparable to that of some moons in our solar system. This realization prompted discussions among astronomers about how to accurately classify Pluto within the hierarchy of celestial bodies. One of the defining features of Pluto is its highly eccentric orbit. Unlike the relatively circular orbits of the major planets in our solar system, Pluto's path around the Sun is significantly elongated and tilted. This elliptical orbit takes Pluto from around 29.7 to 49.3 astronomical units, AU, from the Sun. An astronomical unit is the average distance between the Earth and the Sun, approximately 93 million miles, 150 million kilometers. The eccentricity of Pluto's orbit adds to its complex relationship with Neptune. Despite being much smaller than Neptune and residing farther from the Sun, Pluto's orbit occasionally brings it closer to the Sun than Neptune. This unique orbital arrangement raises questions about the potential for gravitational interactions and collisions between these two distant worlds. The orbital periods of Pluto and Neptune also highlight their unique dance around the Sun. While Pluto takes about 248 Earth years to complete one orbit, Neptune orbits the Sun once every 165 years. This difference in orbital periods means that Pluto and Neptune occasionally come into proximity, but without colliding due to the gravitational influences of other planets and orbital mechanics. The gravitational relationship between Pluto and Neptune is governed by complex dynamics, including their masses, distances from the Sun, and orbital speeds. Despite their occasional close encounters in orbit, these celestial bodies follow predictable paths due to the principles of celestial mechanics, elucidated by Isaac Newton and refined through subsequent scientific advancements. The stability of Pluto's orbit amid its eccentricity and interactions with Neptune can be attributed to several factors. One crucial aspect is the gravitational influence of larger planets such as Jupiter and Saturn. These gas giants exert significant gravitational forces that help stabilize the orbits of smaller bodies, like Pluto, preventing them from drifting into unstable trajectories. Additionally, the three-body problem, a fundamental concept in celestial mechanics, helps explain how Pluto's orbit remains stable over long timescales. The three-body problem involves understanding the gravitational interactions between three celestial bodies, such as Pluto, Neptune, and the Sun. This problem is mathematically challenging, but it provides insights into the complex interplay of gravitational forces that govern Pluto's orbital behavior. While the possibility of a Pluto-Neptune collision has sparked interest and speculation, it is essential to approach this scenario with a scientific perspective. The intricate dynamics of celestial mechanics suggest that such an event is unlikely to occur in the near future. However, continued research and advancements in astronomy may provide new insights into the long-term stability of Pluto's orbit and its interactions with other celestial bodies. The recent discussions by astrophysicists Neil deGrasse Tyson and Michio Kaku have brought renewed attention to Pluto's status and its potential cosmic encounters. Their insights underscore the importance of studying celestial bodies beyond our immediate cosmic neighborhood, as understanding their behavior contributes to our broader knowledge of the universe. In conclusion, the case of Pluto exemplifies the complexities and wonders of celestial mechanics. Despite its reclassification as a dwarf planet, Pluto continues to be a subject of fascination and study. Its unique orbit, interactions with Neptune, and potential for future cosmic events highlight the dynamic nature of our solar system. Through continued observation and research, astronomers strive to unravel the mysteries of Pluto and other celestial bodies, deepening our understanding of the universe and our place within it.